Let's continue with the next chapter, chapter 2, and this is still under the consumer theory, but this time we're talking about uncertainty in consumer theory. All this while, when we talk about consumer preference, we have seen that all the consumer preference that we have discussed in the previous videos, video number 1 and also 2, shows that the outcomes is realized, each of the outcome is realized with certainty. What happens if the outcomes, each of them, is realized with uncertainty? That means the outcome exists, but whether we get it, whether we realize it or not, is uncertain. So this is basically referring to uncertainty in the consumer theory. So like I said just now, all this while we have assumed that consumer acts in a world of perfect certainty. But now we want to relax this assumption. We want to consider uncertainty in the consumer preference. There are a lot of examples in our daily life that involves uncertainty. For instance, you know that you're taking a certain number of modules this semester, let's say 3 modules: microeconomics, macroeconomics, and also econometrics. I'm just making an example related to you as students. It is certain that when you take final exam or perform or write any assessment and then submit to lecturers, in return, you will get or you will receive certain results in the end of the semester, isn't it? Those results are in the form of grades. If you're excellent, then you can get A or A minus at least. Or you can get B plus. Or you can get B, so on and so forth. If you don't perform well, then you may fail the subject or the module. So let's say in any department, let's say we have these grades: A, B, C, and D. I'm just trying to make it simple. And actually, in the IIUM, we have more than this: A, A minus, B plus, B, B minus, so on and so forth. But this is for the sake of example, I make it simple. So you can see that if you take 3 modules, let's say the first one is micro, like I said just now, and the second one is macro, and the third one is econometrics. Okay, so for each of the module, at the end of the semester, when the results is released after you submit all of the assessments, regardless whether it is final assessment or final exams or project paper, then in return, you may get either one of these outcomes. Okay, so for instance, let's talk about one module only for simplicity. So A is a certain outcome, B is also a certain outcome, C is also a certain outcome, D is also a certain outcome. But what is not certain is whether you realize A for your results or not for micro exam or for micro modules. Whether you realize B is the results or not for your micro grade here. Same goes to C, same goes to D. So here, taking micro here is actually like gambling, because you're not certain in terms of like realization of the outcome. You are certain with the possible outcomes, because you know that all of these outcomes are possible, but you are not certain about its realization, whether you can get A, B, C, or D. So all of these in terms of realization is not certain. So when it is uncertain, then there's a probability attached to it, isn't it? What I mean here is there's a probability attached to each of the outcome. So let's go back to this. Let's assume that any consumers are assumed to have a preference relation over gambles instead of consumption bundles. So let's say you have A here. A is basically a set that consists of what? A set of consists of outcomes or the results of the gambles. and it is finite, means that you know exactly how many outcomes you can have in the set of A. So in our case here, the outcome here could be A, could be grade B, C, and D, isn't it? So each of the outcome here, you put in one place, we call it set A here. This is set A. So capital A here is A1, A2, A3, and A4. So we can see here AN here is referring to A4. That's how we read it. And it's finite because the outcomes here is finite, exactly 4. We know exactly the total number of outcome. So it is not infinite. Okay. But here, the AIs involve no uncertainty, like I said just now. But it is not clear which of these outcomes is realized. We don't know, even if you work so hard for your assignment and also project paper, but if you don't work smart, probably you can get D. You realize D for your grade. Probably the most you can get is C, or you realize a C for your grade, A3. You get what I mean? So, of course, A, B, C, and D are certain, but then, whether you realize A or B or C or D is uncertain. That's why for each of the outcome here, there's a probability. Okay, so I refers to 1, 2, 3, and 4. Okay, then for each of the outcome here, we have probability Pi. Okay, such that I also the same like this. So probability, if you're very hardworking, just imagine, if you're very hardworking, the probability for you to get an A, so P1, is actually 0. Let's say 7. This one 0.2. This one 0.08, for instance, and P4 0.02, for instance. Okay, so Pi denotes the probability that outcome AI is realized. Alright, now if we try to put all of this in a formal way, so in formal way, it can be defined as in definition 1. Let's look at definition 1. Definition 1 says that let A is a set of outcome, which is finite set of outcome that consists of A1, A2 until AN outcomes. Then GS is another set. What is a set of GS? It is the set of simple gambles on A, which is given by this expression. Now, so GS is actually a set of simple gambles. So when we say a set of simple gambles, that means each of the outcome in A here, we associate with its own probability. And in this case, you can see GS is actually the set of P1 as a composite of A1 until Pn, probability of outcome N, is a composite of AN evaluated at probability I, which is greater or equal to 0, and the sum of all probability is 1. Now, let's look back at this example. So that means GS in this case is actually the set of what? If we look at this notation, we can see that the set of P1 is composite of A1, P2 composite of A2. Let me erase this, is a mistake, typo. Right, A2, and then we have P3 composite of A3, and then the last one we have Pn composite of AN, right? Evaluated at the probability greater or equal to 0, and we know that, as you can see here, if you sum all of them, okay, let me put evaluated at. Let's go back to the notation. What else we need to put? Yes, instead of putting a vertical bar, we need to put comma here because I want to describe the set that we have here. That means the sum of, Pi has to be equal to 1. That's it. And the sum of probability is equivalent to 1 because we don't miss any single possible outcome. In this case, let's say this university only have this kind of grade. How many grades? 4 grades, A, B, C, D. We don't miss any other grades. If we allow this university to have A minus, that means we miss this grade, isn't it, in the set here? Okay, so let's go back to this. But you have to take note that when one or more of the PIs is 0, we can drop those components from the expression. Now, let's go back to this example. Like I said just now, if this university only consider A, B, C, D as the grades, then we don't miss any single outcome, isn't it? So when you add all of the probability here, then it becomes 1 like this. However, let's say this university also consider A minus, but the probability for you to get A minus is, let's say, 0. P, let's say, 5 here is 0. Then you just need to omit this. So that's why this is what it means by this statement. Okay, so when one or more of the PIs is 0, we can drop those components from the expression. Now, if you look at this example here, that the example that I used just now, this is the set of simple gambles. However, sometimes we can see that there's a case where when you play a gamble or when you involve in any kind of situation that involve gambling, okay, the results of the outcome itself or the price or the payoff is sometimes gambles itself. So let's say somebody comes to you and say to you, if you do a business, okay, so you do a business, and then he says to you there are 3 possibilities. Number 1, you can have break even where profit is equivalent to 0, and then this is outcome 1. Secondly, you can have positive profit. So here profit greater than 0. Let's call this one outcome 2. And then the third one, you can have a loss. You can lose the the business, and then the profit here is negative losses. Yeah, all right. And then this one is A3. Right. And then he says to you, okay, take this gambling. When he says take this gamble, do this business. The business is also a kind of gamble in literal sense, because you are not so sure that you can realize break even, positive profit, or losses, isn't it? So in that sense, it looks like a gamble. Okay, but I'm not talking about the gamble of lottery and whatnot. Yeah, I'm just talking about gambling, because I relate it to gambling terms, because the results here, the realization of the result is uncertain. So here, and then he says to you, if you can get at least break even or positive profit, and then I give you another outcome or another results or another payoff, which is another business for you to set up. And you know that if you set up another additional business, you can also have 3 different outcomes: break even, positive profit or losses. Then such kind of gambles are called compound gambles. Okay, a very typical example in the textbook in Western countries is that they always refer to lotteries. So in some lotteries, one can win monetary prizes, yeah, but also tickets for another lottery. And if you have, if you get another ticket for lottery, then you can have, win or lose also. So the result is uncertain. So it becomes a compound of the existing gamble. So for simplicity in this module, we are trying not to talk about this kind of gambling. So we rule out infinitely layered compounds, gambles. Now, so you have seen the definition here. Let me repeat again the definition. Let me erase some mess here so that I can focus on the definition. Right. If you look at the definition 1 here, let me repeat it again. Definition 1 says that let A is an infinite a set of outcomes consists of A1, A2 until AN outcomes. Then if we have another set here, call it GS. This GS is actually the set of simple gambles on A, which is given by this expression. Okay, and this expression, like I said just now, GS consists of probability 1, which is composite of, this is composite of outcomes A1 until probability of getting realizing an outcome as a composite of AN, okay, such that each of the probability of each outcome must be greater or equal to 0, and the sum all of them, if you don't miss any single outcome, it should be 1 or 100%. Now if you look at this term, P1 composite of A1, this is a very simple term, because if I show you the example here, very typical example in mathematics, basic mathematics. So if I have, let's say, f consists of 2x minus 1, and then I have g as a function of x consists of 3x plus 2. And let's say I say to you, f is a composite of gx. Alright? Now when f is a composite of gx, it can be also rewritten as f as a function of g as a function of x. Now if we go to this specific example here, how do we rewrite it? Then we can rewrite it this way. 2 multiplied by a function of gx minus 1, can you see? And 2, because you see gx here, take gx here, substitute it back into second line here, then you can have something like this. 3x plus 2 minus 1. You solve it. Okay, there are some steps here I don't want to show you because it's too simple. Then you can get what we call 6x plus 3. So this one is actually this, can you see? So this is basically what we call composite function. Alright? Like I said just now, for this module, we only concentrate on simple gambles. But we know that we can have simple gambles and also compound gambles in reality. In order to understand more about gambles or choice under uncertainty, we need to look at the axioms or the properties of choice under uncertainty. So we know that, like I said just now, we have, a set of gambles which consists of simple and compound gambles, but we only want to focus on simple gambles. So from this set of gambles that consists of simple and compound gambles, we want to see certain properties or axioms so that all of this set of gambles can be boiled down to simple gambles only. Alright, now, so let's say we have a set, call it G, which is this one, and this G denotes the set of all gambles, including simple and compound gambles. Let's say in set of G here, capital G, we have a gamble. Call that gamble G, small letter g. So G here is an element in the set of gamble capital G. And then this G, okay, we take, if I draw it in this way, we have the set of gamble, inside here we have G. So this gamble, okay, a gamble here can be described as certain outcomes with their associated probability. In particular, probability 1, composite of a gamble associated with outcome 1 until probability of K associated with gamble of outcome K, such that K is greater or equal to 1. So if we have G subscript I here refers to outcomes, of a gamble or outcome itself. And if I say outcome of a gamble, the gamble could be compound gamble or simple gamble. So as mentioned before, if we have a consumer, that particular consumer is assumed to have preferences, and that preferences is denoted as this, which is at least as prefet 2 over the set of G, the set of gambles. So like I said just now, in order for us to understand more about the properties of choice under uncertainty, we need to understand the axioms or properties of choice under uncertainty. There are about 6 axioms. The first and the second axioms are very simple because you have seen this kind of properties in the consumer theories for certain utility function. So let's look at the first axiom. First axiom says completeness. If we have a set of gambles, call it capital G, and then in this set of gamble, okay, we have gamble G and gamble G prime, and both of them are within this set. So either G is at least as prefet as G prime, or G prime is at least as prefet as G, or both. Now let's look at axiom 2, transitivity. So let's say we have 3 gambles, G, G prime, and G double prime, and all of them are basically gambles in the set of capital G. So I have G double prime here. So if let's say we say G is at least as prefet as G prime, and also G prime is at least as prefet as G double prime, then we can say that G is at least as prefet as G double prime, isn't it? So this is transitivity. So we have seen the first and the second properties. Now let's move to the third properties. But before that, carefully note that each outcome in the set of all outcomes A is represented in G, isn't it, as a degenerate gamble. So for each of the outcome here, instead of outcomes, in a set of infinite outcome, if you can remember in the second slide earlier, I already mentioned this. So when we try to associate each of them with probability, which is represented in a set of G, capital G, then this G is basically degenerate gamble. Okay, so the two axioms imply that the elements in A can be ordered by at least as prefet 2, isn't it? Okay, so if we have G here, we have G, G prime, G double prime. You can order them based on preference relation using this. And if you have equal sign, it is weakly prefet. If you don't have equal sign, like this, then it is strictly prefet, isn't it? So, because each element in the set of outcomes A is represented in G as a degenerate gamble, and because we follow axiom 1 and 2 previously, then we assume that these elements have been indexed such that outcome 1 is at least as prefet as outcome 2, at least as prefet as outcome 3 until outcome n. Let's crack on. We move to axiom number 3, continuity. So this axiom or this property says for any gamble G which is element in set of G, capital G, there is some probability, and that probability we call it alpha, which is between 0 and 1 inclusively, such that this gamble G is an equivalent relation. This sign means an equivalent relation of what? Probability alpha composite of outcome A1 and 1 minus alpha composite of outcome AN. So this is continuity. Axiom 4, monotonicity. So if we have all probabilities, alpha is between 0 and 1, isn't it? So if alpha is between 0 and 1, 1 minus alpha here, let's call it beta. Let's call it beta for simplicity. And let's say we don't have any other probability for simplicity. So for all probabilities, alpha and beta, which is between 0 and 1 inclusively, then alpha is a composite of outcome A1 and 1 minus alpha composite of AN is at least as preferred as beta as composite of A1, 1 minus beta composite of AN if and only if, this one means if and only if alpha is at least, alpha is greater or equal to beta. For simplicity, I said this, but is it possible that if we have alpha, let's say 0.7 and beta 0.7, it's possible because both of them, each of them separately, still between 0 and 1, isn't it? So that's possible also. All right, so here, if we look at axiom 4, what does it mean? When we talk about monotonicity, it implies that A1 is at least as preferred as AN, isn't it, in this case? Okay? And monotonicity, it means, let's say we make a line like this. A1 is here, AN is here. If AN is assumed to be here, and we feel that AN outcome is less in terms of money we receive compared to A1, so A1 is at least as preferred as AN, isn't it? Okay, and in this case, because of this sign, so decision maker is not indifferent between all outcomes in A, isn't it? What does it mean by not indifferent? They are different between all outcomes in A, the way they look at it, yeah? All right, so let's move on. We look at axiom number 5, substitution. Let's say we have a gamble, and that gamble is G. And remember, G is actually the set in all sets of gambles, isn't it? So if G is actually probability of outcome 1, it's a composite of, gamble 1 of outcome 1, until probability of outcome K is a composite of gamble of outcome K, and we have another gamble, which is H. H here is probability of outcome 1, the composite of gamble outcome 1 until H. Okay, both of them, G and H, are gambles, yeah, a kind of gambles are in G. So if we have G here, so we have G, we have H, we have G prime, we have G double prime, something like that. Okay, and if G superscript of I is an equivalent relation of HI for every outcome I, then G is an equivalent relation of H, isn't it? Let me erase this bit first. Sounds confusing? You can only understand more on this if you do exercises, yeah? For the time being, I'm explaining to you the theoretical bit of choice under uncertainty. So let's look here. So let's say you're a consumer or decision maker and you are indifferent. What does it mean by indifferent? Indifference means if I give you A and B, I would ask you, which one do you prefer? You would say you can give anything to me. I don't mind anything. I don't mind A or B. I don't mind. So you are indifferent. You have the same preference towards A and B. So let's come back to this. If a consumer is indifferent between the realizations yeah, of one gamble and another, okay, and the realizations occur with the same probability, what more if it is with the same probability? Yeah? Let's say I have gamble G and gamble H, okay, and both gambles, if I play or if I take action, both of them have the same probability to get the results. So let's say this one is 0.5, 0 one is 0.5, or 0.7 or 0.7, up to you, as long as they are the same. Okay, then the consumer is indifferent between these two gamble because the probability is just the same and the realization is just the same. Then I won't mind which one comes first to me, isn't it? Because the result is just the same. That's what it means. But then if it is in a compound gamble, one can calculate the effective probabilities of the single outcomes in A. Okay. So for any gamble G, which is an element in capital G, the set of G, a probability of outcome I denotes the effective probability assigned to AI outcome by gamble G, then what we can say is that Gamble G induces the simple gamble of what? Of probability outcome 1, composite of outcome 1, until probability of outcome n, composite of outcome m, which is in the element of GS. Let's look at the final axiom so that from here we can see how it is boiled down from, very general gambles to simple gambles. So the final axiom states what? States that consumer only really cares about the effective probabilities a gamble assigned to the single outcomes in A. Okay, so axiom 6 says that how we can reduce all different types of gambles here using axiom to simple gambles. So for any gamble, call it G, which is an element in set of G, capital G. So if we have this, okay, and this is the simple gamble induced by G, then this one is actually an equivalent relation of G. So by this axiom and transitivity and the rest of the axiom, a consumer or a decision maker's preferences over all gambles are basically determined by the preferences over simple gambles only. So we only focus on the simple gambles. If we have preferences that obey all of these six axioms, then we can actually represent these preferences in the form of a function, and that function is continuous and real value function. And call that function as U. So U is actually a function in which a set of gamble G is mapped into R. That's how we read this notation, yeah? Or actually, in a very simple form, this can also be rewritten as real number is actually a function of G. Okay, so this function, real valued function, describes a utility function representing what? At least as preferred as on set of gamble G, capital G, yeah? That means for every gamble which is an element in set G, utility of gamble denotes what? Denotes the utility number assigned to G, gamble G. So that means, similarly, if we have UAI, it actually denotes the utility number assigned to the degenerate gamble, that is 1 as a composite of outcome AI. So this one is therefore, we call it utility of outcome AI. Now let's look at definition 2 to be more formal. The utility function of U in which G is mapped into real number R actually has the expected utility property if for every gamble G which is in the set of G, capital, we have this. This is actually U of G, which is the sum of probability of each outcome multiplied by the utility of each of the outcome. And we already know that Pi is this, isn't it? And because Pi is this, therefore, it is actually the simple gamble induced by a gamble, call it G, small letter G. So if we have U, function U actually assigns to each gamble the expected value of utilities that might result, right? Now, so whenever we have a utility function that possesses the expected utility property, yeah, then this kind of expected utility property, maybe some of you have heard it before, is what we call von Neumann-Morgenstern utility function. So whenever we talk about VNM in short, or von Neumann-Morgenstern utility function, it is basically an expected utility. Okay, now let's look in a formal way in theorem 1. So let's say let preferences at least as preferred as over gambles in set of G satisfy the above axioms, the above 6 axioms. Then that means there exists a utility function, call it U, in which the set of G, the set of gambles, is mapped into real number R, representing at least as preferred as on G. Okay? So here, this utility function is actually having the expected utility property. Now, if we have this kind of theorem, what's the implication? So because we have all of these 6 axioms, so an individual can assign utility numbers to outcomes in A. Remember, A is the sets of outcomes, such that the decision maker or the consumer prefers one gamble over another if and only if it has a higher expected utility, isn't it? Now, don't be confused between utility and expected utility, yeah, because expected utility is the expected satisfaction that you can get if you involve in certain, event or action or gamble, for instance. And this kind of implication is logic, because the higher the expected utility you get, the more you prefer that gamble, isn't it, over the other gambles. Now, let's look at the proof. And the proof here is quite long because we want to prove that, we have the expected utility property for a utility function that, possesses von Neumann-Morgenstern utility function. We want to prove theorem number 1. And when we want to prove theorem number 1, we need to show that all of these 6 axioms or properties have been fulfilled. All right, now let's look at the proof step by step. So what we need to do is that we need to construct a function, and we need to show that this function that we are constructing, that we are about to construct, possesses the desired properties or the desired axioms that we have talked earlier. So let's say we have an arbitrary gamble, call it G, and this G is a set, is actually the element in the set of all gambles, call it capital G. And then let's say we have the utility of this gamble, call it UG, and these two satisfy the following, such that this gamble G is an equivalent relations of this. Okay, equivalent relation of this, that is utility of G is a composite of outcome 1 and 1 minus utility of G composite of outcome N. Okay, so the first thing, by the property of continuity, if you can remember first axiom, so such number exists, yeah, and by monotonous A, it is unique. Unique means you only have one kind of results or one kind of satisfaction. So we have derived a real valued function U on G. That's how we do it. Now, let's crack on. So here, we need to show that utility here represent at least as preferred as, okay, so we need to consider 2 arbitrary gamble, call it G and G prime. Both of these gambles are the element in the set of all gambles, all right, and supposedly we have G, if we compare with G prime in terms of preference, G is at least as preferred as G prime. Okay, and here, if we want to confirm with transitivity properties, so by transitivity and the definition of U that we have met earlier, this equivalently equal to what? This equivalently equal to this. So you look at the way I write it carefully. UG, composite of outcome 1, comma 1 minus UG, close bracket, composite of, composite and not at, composite of outcome N, okay, the whole thing in bracket, is at least as preferred as, I put it here, another one here because I don't have enough space, UG prime, composite of A1, 1 minus UG prime, composite of AN. Okay, can you see? So from here, by monotonicity, that means this is actually equivalently equals to UG is better or equals to UG prime in it. Okay, so this one shows transitivity by the definition of U, we get this one. And then by monotonicity, this is equivalently equals to this, right? So let's crack on. We need to show the last one, how U, let's say we have U here, this utility, has the expected utility property, because previously what I have done in terms of proving is to show you how the expected utility here has the properties that I have explained to you in the axioms, the 6 axioms. So let's move on. In order to do this, we have to assume this, yeah? So let's say we have a gamble G in a set of capital G, and then this gamble G is an arbitrary gamble, okay? And then we have GS, okay, which is an equivalent relation of probability of outcome 1 as a composite of outcome 1 until probability of outcome n as a composite of outcome n, okay? And then this is actually in the set of simple gamble, okay? So here we try to reduce our analysis from all types of gamble to simple gambles. That's what I'm doing. So it has been reduced to simple gambles. So by reduction to simple gambles, then we can have, you know, G here as an element of simple gambles, okay? And from here we can have the utility of gambling G here, an arbitrary gamble, that's actually equals to utility of simple gamble, isn't it? Now, what is the next thing that we need to do? So our role now is to show that we must show this. Utility of simple gamble is actually this, okay? So I'm sure you have seen this just now. PIU and AI. We have to show that this on the left hand side here is equal to the right hand side. So how are we going to show this? Now listen to my words one by one. So here, by definition, we have utility of outcome 1. Let's say we have a lottery, or we say we have a business, for instance, and you know that the business, the possible outcome, let's say 3, okay? Profit, losses, and also break even, isn't it? If you have a lottery, either win or lose. So AI here refers to either one of these. So because we have 3 here, so n is 3, isn't it? For this case, n is 2 in it. Alright, so let's say we have utility of outcome AI. For the lottery, this is the price. For the business, this is these are the list of the prizes. Okay, so UAI here satisfies this, such that outcome AI is an equivalent relations of this. Look at this, yeah? Utility of AI is a composite of outcome AI, and also 1 minus utility of AI, composite of outcome AN. Okay? And then this is identical to, let's say, we use one notation only, QI, okay, for simplicity, so that we don't have to write it very long. All right, now, the next thing, by substitution, okay, if you can recall back the axiom, there is one axiom, call it substitution axiom, isn't it? So if we use that axiom, then by substitution, simple gamble is actually this, isn't it? If you can recall back, simple gamble is this, P1 composite of A1 until Pn composite of An, and this simple gamble by substitution is actually what? It's actually an equivalent relation to G prime, and G prime, I can write it this way, P1 composite of Q1, Q prime, or Q1, not Q prime, let me erase it, otherwise you get confused. So here, Q1 until Pn Qn, and this one is actually equivalent to G prime. So here GS, what I mean here, GS is equivalent, an equivalent relation to G prime, and we have GS as this and G prime as this. This is what I mean. So we are using substitution axiom here. So from here, what we can say is that, look at this, G prime. So the simple gamble induced by G prime is actually what? The simple gamble that is induced by G prime is actually this. G prime equals to, look at this carefully. I put square bracket here, the opening, and then I have this, the sum. Let me write it first, then I explain it to you. 1 up to n, PIU, AI, okay, close the bracket, composite of AI, and comma, circle bracket open, 1 minus the sum of I1 until n, PIU AI, composite of AN, okay, close the bracket, and close the square bracket. Okay, so that is G prime. Right, now, and then next, by reduction to simple gambles, okay, remember the last axiom is the simple gambles, and also the transitivity, okay, this is the third or the second, axiom, then we can have GS is an equivalent relation to G prime, also the equivalent relation to GS prime. GS refers to simple gambles, yeah. When you see subscript S, it refers to sample gamble. So here, by reduction to simple gambles and transitivity, then we can have GS is an equivalent relation to G prime and also equivalent relation to GS prime. Or we can also say this, okay, GS is actually equivalent to, I open the bracket, let me rewrite it. Let me write it first. So the sum of I equals to 1 up to n, PIU, AI close, okay, and then close the circle bracket again, composite of A1, comma, open the circle bracket, 1 minus the summation of I equal to 1 and PI, UAI, right, and close the bracket, composite of A, and then close the circle bracket. So here, again, I repeat, by reduction to simple gambles, which is the last axiom, this reduction to simple gambles is the last axiom, and the transitivity, which is the second or third axiom, if I'm not mistaken, then a GS is actually an equivalent relation to G prime, and G prime is actually an equivalent relation to GS prime, isn't it? Okay. Or we can also say this, such that GS is actually this, okay, in a square bracket, it is this as a composite of outcome AI, and also this as a composite of outcome AN. Alright, now next. So by definition, therefore, utility of simple gamble is 10 is a unique number. And this unique number satisfying what? It satisfies this, GS is an equivalent relation of, okay, look here, UGS, composite of A1, AI, or A1, okay, and then here 1 minus UGS, composite of AN. Close bracket this. Alright. Before I proceed, let me make some correction because I think I have made some mistakes here in terms of notation. So look here, this AI, it shouldn't be AI, it should be A1. Otherwise, it's not comparable with the previous, GS prime, and with this, the last one here. Also, let's go back to this. Also, the same thing here, yeah. I'm talking about this basically. I should change it to A1. Otherwise, it's not comparable. And you can't do proof like this when it is not comparable. So one. All right. Now, what we need to do, we are about to end the proof. You look at this, I call this one A, and look at B here, I call this one B, okay? By comparing between A and B, you can see A1 here, and also A1 here, and here, and also and here. Let me use different pen, let's say yellow, okay? This one, and this one. So they are comparable, isn't it? So what about this? This and this. How can we do this? Because we have this. Substitution. Remember the axiom of substitution? So this one, obviously, can be compared with this, isn't it? So here, because of that, that's why we can have, this as this, and this as this, isn't it? GS is this. GS is a an equivalent relation of utility of GS, simple gamble, composite of outcome A1, comma, and also 1 minus utility of simple gamble, composite of AN. We can also write it with GS prime, UGS prime, here 1 minus UGS prime because of this. You get what I mean? But we use this only, so because they are just the same anyway, equivalently. Okay, so by comparing A and B here, therefore we can obtain this. So finally, we can obtain this. UGS, okay, is actually the sum of I starting from 1 until n, PI, U, AI in it. Okay, so this is the utility of the expected utility, okay, or von Neumann-Morgenstern utility function, because this one is actually this. That's why we can write it here, which is equivalent to this. So, proven. QED. Alright, now you already know that the von Neumann-Morgenstern utility function is actually the expected utility, and although you have seen 6 axioms previously, but be careful, note that von Neumann-Morgenstern utility functions or expected utility are actually not unique. So that means we can actually have infinite number of preferences that can be represented using the same von Neumann utility functions. And because of that also, because of the expected utility property, so here we cannot have positive monotonic transformation all the time. We can still have, but not all the time. So let's look at theorem number 2 here to make it, more formal in terms of the characteristic of von Neumann-Morgenstern utility function. So suppose the von Neumann-Morgenstern utility function, which is denoted as U dot here, represents at least as preferred as. So then the von Neumann utility function, okay, another von Neumann utility function represent as V dot here, represents those same preferences if and only if for some scalar, for some constant, and call that constant alpha. Let's say alpha is 5 or alpha is 0.5 because it's a constant, yeah, and some other constant scalar, okay, that has to be positive, call it beta, okay, then we can have this relationship here between V and also U for all gambles G. Alright, Now, we can represent, different types of preferences infinitely, okay? Because expected utility is actually identical to positive affine transformation or linear transformation. Alright, now, how to prove this theorem number 2? What I want you to do is, this is becoming your homework. I won't check it. And listen carefully. I may ask in quizzes, in any quizzes, or in any assignment. So I want you to do your own homework to study about this theorem. Now, this theorem for von Neumann utility function is very famous. Therefore, it's very easy to find different ways of proof for this theorem. You can check, and all the resources are available from the internet, but you have to find something that you can understand. Okay, so let me guide you. The first thing is that try to learn what does it mean by positive affine transformation in a very simple way, using undergraduate level of explanation that you can find from the internet. Okay, because nowadays it's very hard to go to the library, isn't it? Now, of course, you haven't, for you, if you're economic students, if you didn't do Bachelor of Mathematics in your first degree, of course, you never heard this thing. Okay, so what you can do is that try to get some YouTube videos from the internet that teach the meaning and also the examples of positive affine transformation in a very simple way using numerical values. At least you get some, idea about the concept of positive affine transformation. And then after that, try to look at the von Neumann utility functions theorem available on YouTube and also on the internet in the form of PDF file and whatnot, yeah, because there are a lot, like I said to you earlier. From there, try to find out the topic about von Neumann-Morgenstern utility function or expected utility function transformation. There are a lot of notes and also YouTube videos that are talking about this, believe me. And then from there, learn how to prove theorem number 2. There are a lot also, like I said to you just now. So this is your independent study. I hope you can start from now, looking at the proof of theorem number 2. Why it is so important to learn proof number for theorem number 2 here? Because if you can learn how to prove this theorem, then from this, process of learning how to prove this theorem, you can clearly see that von Neumann utility functions or expected utility functions are actually not unique, not completely unique. And then they are not entirely ordinal. Remember, the word ordinal comes from the root word order. So they are not entirely can be ordered, and they are not completely unique. It means von Neumann utility functions are not completely only if you have preference A, you can have many von Neumann utility functions. You get what I mean here? So that's why it says, okay, von Neumann utility functions are not completely unique. Some of them are unique, some of them are not unique. And also, we should not attach unwanted importance or undue significance to the absolute level of Gamble's utility. Yeah? So here, for instance, it is not possible to use these expected utility functions for interpersonal comparisons of well-being. Why? Because like I said earlier, sometimes you cannot order it. So when you cannot order it, it's not easy to say which one is better than this one, which one isn't it? And they're not completely unique because there are so many with the same preferences, for instance. Okay, now, okay, put aside this, what we want to see now is that we want to analyze the relationship between von Neumann utility functions and the consumer's attitude toward risk. And this is very important because why we need to relate this with risk? Everybody knows that when there is a risk, there is uncertainty. When there is uncertainty, then you have to expect what would happen later. Then you have so many possibilities. I expect this, plan A, plan B, plan C. All right? So that's why von Neumann utility function is always used to relate with the consumer's attitude towards risk. So let's say we want to confine attention to gambles. Like I said earlier, gambles can be business, can be lottery game, can be anything as long as the realization of the results or outcome is not certain. Okay, so we confine our attention to gambles whose outcomes consist of different amounts of wealth. Call it W. So this is wealth, yeah? And then we assume that the set of outcome, call it A, is actually the positive real number. Okay? So here what we mean here is that if we do business, the outcome is always positive, not negative. Which is logic also, especially when the business is a very long-term business, very stable and whatnot, isn't it? So we don't expect to have zero profit or negative profit or losses in it. Okay. And additionally, we only want to consider gambles giving finitely many outcomes, a strictly positive effective probability. So those outcomes that we want to consider in a set of gamble, for instance, we only consider those outcomes with positive effective probability. That means any outcome with a zero probability of realization we don't consider, because it's just you put it there, you write it again there, the answer is always zero in it. Okay, now, and also we assume that the utility, okay, to be strictly increasing and twice differentiable for all wealth level. Twice differentiable means what? If you differentiate this one time, and then after that you get the answer, and then that answer you can still differentiate it and give you another answer. So that is twice differentiable. So why do we need to have this kind of assumption? Because mathematically speaking, if we have strictly increasing utility function and twice differentiable, then the answer is always there. Okay, mathematically speaking, because we want to make sure that the arithmetic operation is smooth and doesn't give you any problems arithmetically. Okay, so now what we need to do is let's look at the next definition about the von Neumann utility function. So let's say U dot be a decision makers or the consumers von Neumann Morgenstern utility function for gambles over non-negative levels of wealth, because we already put this assumption. So this time the gambles doesn't give you any losses or zero profit, for instance. Then for the simple gamble, you already know the simple gamble notation looks like this. The decision maker or the individual consumer is said to be what? We have three different types of behavior of consumer here. Number one, risk averse. Number two, risk neutral. Number three, risk loving. So a consumer is a risk averse person at gamble G if what? If the first one here is greater than the second one here. What does it mean by the first one here? The first one here is actually the expected, the utility of expected value of the gamble. You see the word, you see the letter U here. It is the utility. Utility of what? Utility of expected value of the gamble. Utility of the expected income of the gamble. What does it mean by UG? You have seen UG earlier. And UG is actually the expected utility of the gamble. Okay, so if if the utility of expected value of the gamble is larger than the expected utility of the gamble here, then the person is risk averse. What about risk neutral? If both of them are equal. What about risk loving? If the first one here is less than the second one. Okay, so here UEG is written as this. UG is this one. So that means, let me erase this mess. So if the first one here is bigger than the second one, then the person, the individual consumer, is said to have risk others. Okay, so I hope this is very clear to you. And if I change the color here, instead of this, it becomes less, then the person is said to have risk, loving at gamble G. But if we have equal sign, then this person is a risk neutral person. Okay, so here we want to relate it with a bit of mathematics. So if we talk about the person who is making decision on a gamble, okay, so the decision maker or the consumer here is number one. We can call this consumer risk averse if and only if IFF, okay, his von Neumann-Morgenstern utility function is what? Is strictly concave. Okay, so risk averse. But the person is said to be risk neutral if what? If von Neumann utility function of this person is what? Is linear. Because of equal sign, isn't it, previously? Now, number 3, let me change this one. Instead of risk averse, we can have risk loving person. If von Neumann Morgenstern utility function is strictly convex. Alright. All of this will be shown in the form of graph later so that you can see clearly why it is said that way, mathematically speaking. Before we proceed to graphing, let's look at this note. Here we can see that a consumer or decision maker is a risk averse person. Okay, so this is number 1. If and only if his von Neumann utility functions or his expected utility function is strictly concave. But he is considered as a risk neutral person if his expected utility, von Neumann utility, Morgenstern utility function is strictly linear. And he is a risk-loving person if the utility function, the expected one, is strictly concave over the appropriate domain of wealth. Alright, now we're going to use all of these to show the point here in the form of graphs. So let's say we have 2 different types of wealth levels, W1 and also W2, small letter. So if we try to put it in the form of utility of this and also utility of this, okay, then we can have UEG here, utility of expected value of a gamble is actually equivalent to utility of this. This is the expected value of gambling, yeah? This is utility, the circle bracket here. And you can see that probability of outcome 1 with wealth 1 and 1 minus P1 wealth 2. Alright? And then utility of a gambling, let's say a lottery or a business, is given by this. Probability 1 times utility of wealth 1 and 1 minus P1 times utility of wealth 2. There are 2 different things, yeah? I'll show you more in the form of graph so that you can see clearly. Basically, once you see the graph, you will recall back what you have learned in intermediate micro 1, basic intermediate microeconomics, yeah? So, when I put it in the form of graph like I said earlier, so let's say here, the first one. So we have the ordinate, and then we have the abscissa. Okay, so this is abscissa, this is the ordinate. Okay, on the abscissa we put wealth, and the ordinate here we put utility of wealth. Alright? So utility of wealth, or let me put it in general so that I can use it for general thing here. Right. So we have two different wealth in it. So W1 and also W2. The utility of wealth number 1 is written as UW1. The utility of wealth number 2 is written as UW2. Do you get me? So wealth 1 gives you, or gives the decision maker, UW1, the satisfaction at the level of UW1. Wealth 2 level, okay, gives the decision maker utility or satisfaction at UW2 level, such that W1 is less than W2. So probably this one is 1K and this one is 2K. I'm just making up it to show it numerically. So let's say W1 is here. Therefore, UW1 is here, isn't it? So we have the first point here. Let's say W2 is here and we have UW2 is here. So we have 2 points. Now join these 2 points to create, one straight line. And let's say we have a curvy curve which is above this line. But this curvy curve connects the first point here and also the second point here. So when we draw it, so it looks like this. And this one is described as UEG. Okay? So between W1 and W2, pick one point along this straight line. Then we can have the average between these two, isn't it? Depending on the weight of W1 and W2 here. So let's call it W bar, for instance. So you can see here, this straight line here gives the utility of, gamble itself, which is given by UG, and UG here is W bar. But on this point, which is above, when W is at W bar, then we can have UEG itself. So here, the curve is curvy curve, and it is called concave, isn't it? And UEG here is concave. And at this point, you can see clearly UEG here is greater than UG. I'm not going to re-explain to you what is UEG and what is UG because it has been explained in the previous slides. Okay. So here, when we talk about UEG, let's go back to this slide. UEG is given by this. Okay. So that means U P1W1 plus 1 minus P1W2, the utility of this, expected wealth here, is actually bigger than UG. And what is UG? UG is given by this. So let me rewrite it again here. Is equivalent to P1 times UW1 plus 1 minus P1 times UW2 in it. Okay, so that's the idea. Alright, now for this case, as you have seen in the previous slide, when UEG is greater than UG, or this term is greater than this term, then this person is said to have risk-averse characteristic. Alright? Then here we can see clearly utility of the expected value of the gamble, or of the wealth in this case, yeah, is actually greater than the expected utility of the lottery itself. So the expected utility of the lottery itself is smaller than the utility of expected value of the wealth itself. Alright, now what about this? I give you another one here. Let's use different color. Let's say red. So if I have this, W here, dot here, again we use the same point, W1, UW1. So we have W2, here UW2. Join these 2 points to get a straight line. Then if we have a curvy curve here, which is below this 2 point but upsloping one, so I draw it like this. It's not nice, let me redraw it again. Right. This is upsloping curve, the same as the first one. Right, so slowly, okay, at least it looks quite sensible to me. But you can see EG is below UG, isn't it, for this case? So let's take one point here, W bar, the average between W1 and W2 wealth. So this one is actually UG, and this one is the UEG. Clearly, what we can say here is that the utility of expected value of the wealth, okay, or the investment in this case, the gamble in this case is the investment, then you can get wealth from this investment, is actually less than the expected utility of the investment itself, right? What about this? So before I proceed, then this one can be changed to less when we are talking about this graph. This is in the form of theory. You can try exercises if you want to apply this theory. I'll give you more exercises later. Now, but if we have this, W1 here, UW1 here, and W2 here, UW2 here, join the 2 points to get a straight line, and here we have UEG is actually the same as UG. Okay, then I change the color here. Instead of having this, we can have equal sign, isn't it, for the third case here. Take the value here. So we have UEG actually equal to UG. In this case, G here is, the wealth itself, yeah. But I use G so that you can compare with the previous slides. But G here is referring to the investment, the wealth investment. Okay, so the first one is what we call risk averse. The second one is therefore the opposite of the risk averse. Here we call it risk loving. And the third one is what we call risk neutral. So this is theoretically speaking when it comes to explanation of risk characteristic in relation to the von Neumann-Morgenstern utility function. What you can do to understand more on this is that to look at some exercises from the internet or the textbook for intermediate level, intermediate level is below than the master level, yeah, because what I'm going to teach you is for master level. So that you can relate those examples that you found on the internet or books with the graph and with all of the explanation that I've explained here in the form, when the level is a bit higher in the, master level. Okay, so here, I'll show you exercises later, like I said earlier. Okay, now, there's another thing that we want to emphasize here, that is the certainty equivalent. Okay, so when we talk about the certainty equivalent of any simple gambles, call it G, over wealth levels is actually an amount of wealth, call it CE, offered with certainty, such that UG equals to UCE. So there will be a risk premium, and risk premium is what? It's an amount of wealth, P, such that UG is identical to U, utility of EG minus P. So from here, we can have this, isn't it? Because you see here, because UG is actually identical to UCE, then this one can be substituted, for CE here. Okay, UCE. So what I mean is this. So UG equals identical to UCE, identical to UEG minus P. You get me? So it's very clear that from this we can imply this as well, isn't it? Because EG minus P is CE, therefore P is what? EG minus CE. Is it clear? Okay. Now here, based on this definition, so we can say that when a person is a risk averse, of course, he prefers more money to less. So we have certainty equivalent is less than EG. So premium is positive. Now, what does it mean here? You imagine if a person is a risk averse, very, to some extent, dislike risk. Of course, that's normal for any human being. So when a risk averse person wants to make a decision on whether to involve in certain gamble or not, by putting his own wealth here, he will only pay some amount of wealth, okay, to that particular gamble. Alright, given that that particular gamble will give him return, isn't it? That's basic, yeah, for any human being. Now, the premium P is positive, means a risk-averse decision maker or person will pay some positive amount of wealth, okay, to avoid the gamble's inherent risk. So that's why for any person that want to invest in certain thing, we know that the outcome is uncertain, but they want the return. In order to confirm with the return, they're willing to pay some amount of premium to be on the safe side. Okay, next. Same thing, yeah, when we have CE equivalent to EG or CE greater than EG for risk neutral and risk loving respectively. To make it more understandable, let's look at a very simple example here. So because we want to understand the concept of certainty equivalent, let's go back to the definition first. Remember, the certainty equivalence of any simple gamble, call it G, over wealth levels is an amount of wealth, so we call it CE, yeah? Offered with certainty, okay, such that UG, or expected utility of gambling, is just the same as utility of certainty equivalent. And the risk premium is an amount of wealth P such that UG is identical to UEG minus P, and so on and so forth. So we know that when we talk about this, we are talking about certainty equivalent, yeah? So expected utility of gambling should be equivalent to utility of certainty equivalent. That means they are indifferent. So here, you are indifferent between, gambling and also taking money, which is very certain, taking money with certainty. All right. Now, let's say you are given this utility function of wealth. So instead of G, we use wealth, yeah? So here I change it to wealth. So here, wealth. All right. So let's say utility of wealth is given by square root of wealth for simplicity. So W here, this is a person's utility. Let's say his name is Ken. W here is Ken's daily income in the form of pound sterling. Ken's daily income in pound sterling. Now, we also assume that Ken's does not have any initial wealth. He only can get income if he works. That's what it means. Okay. Now, then, at the same time, he is offered the following gamble. And the following gamble is, with the probability of P1 to get a pound sterling per day. And 1 minus P1 probability to get what? To get B pound sterling per day. Okay. So here, the certainty equivalence is actually a certain amount of, pound or quid that makes Ken's indifferent between gambling and taking the money. Okay, that means the utility of money, okay, is equivalent to the expected utility of gambling. So this is the concept of certainty equivalence. Now let's use a numerical example. Yeah. So the expected utility of gambling, or wealth here. Let's say this wealth here is in the form of lottery. The gamble here is in the form of lottery. Is actually, if you can recall back previous slides, is P1 UA1 UA, not UA1, UA plus 1 minus P1 utility of getting B pound. Okay, so we know that utility function look like this, and therefore if we specify it further, then we can have something like this. P1 square root of A plus 1 minus P1 square root of B. So let's say we put numbers so that you can see clearly what does it mean by all of this. Let's say P1 is 1/3, therefore 1 minus P1 is 1 minus 1/3, 2/3 in it. Also, let's say A is equivalent to 9 pound and B is equivalent to 81 pound. So if you put it back into this utility function, the expected utility of gamble, or the wealth here, then you can have something like this. Okay, 9. I can also rewrite it this way, and this is simple maths. 1 minus P1, which is 2/3 times square root of b. So if you simplify it and try to get the answer, you get this 7 in expectation. So now what we need to do is that to find the certainty equivalence, or CE, that gives the same utility, which is 7. Because expected utility of gambling here is 7, and we say that expected utility of gambling here must be equivalent to utility of certainty equivalent. So that means if here is 7, utility of certainty equivalent must be 7 also in terms of unit, isn't it? So we need to make sure that this is 7. So from here, we want to find what is actually CE that can give us 7 utility satisfaction. All right? So that's the issue now. And also, recall back that we are given this utility function. So, let me rewrite it again here. UW equals to square root of W equals to 7, because we got the answer 7, isn't it? So then from here, we know that it has to be equals to U CE. And from here, we can have something like this. W equals to 7 squared, isn't it? So that means W here is equal to 49. Okay? So since UW, the expected utility of gambling here is 7 and equals to the utility of certainty equivalent, which is 7 also, then the value of wealth must be 49. And this value of wealth is actually CE, that gives utility 7. Okay, is it clear? Alright, now the next thing is, here I didn't even talk about premium. Okay, now, so in this case, if we want to talk about risk premium here, then we need to calculate it. From there, we can detect whether Ken is risk-averse person or not. Alright? Now, if Ken is risk-averse, then we know that the risk premium has to be positive, isn't it? Now, before I proceed to the calculation of risk premium so that we can check whether Ken is a risk-averse person or not, let me give you something here. So here, if CE is 49, give you utility equivalent to 7. So what is the expected income for this gamble? If we know that, then it can help us to find risk premium. So let's crack on. Okay, so let me rewrite it again here. CE equals to 49. And then we know from the lecture note just now, look here, risk premium P is equivalent to the expected value of gambling or welfare in our example minus certainty equivalent. We know certainty equivalent is 49. We don't know what is risk premium value. We still have yet to find the expected value of a gamble or wealth or lottery. Okay. So now, because CE has been found, we need to find EW, isn't it? So it is very simple. We have P1 equals to 1/3. Okay, we have A equivalent to 9, isn't it? P1 minus P1 equivalent to 2/3. We have found it earlier, B equivalent to 81. So if we play this kind of gambling or lottery, the expected income that we can get is what? So 1/3 times 9 plus 2/3 times 81. It gives us very easy 59. So from here, you can find the premium is EW minus CE. And in this case, 59 minus 49, which is 10. What's the value here? It's obviously, it's not negative. It is more than 0. So if you go back to this slide, it says what? If we have, CE is less than EG or EW in our example, then our P here is 0. Now, so in this, P here is greater than 0, yeah? So here we can see clearly P here is greater than 0, and it indicates that Ken is a risk-averse person. All right? So here, Ken is a risk-averse person. All right? Now, let's try to put all of this in the form of graph so that you can see clearly what I did see just now. So here, if I erase this so that I can have some space. Okay, so I want to show it in the form of graph. Because we know that this person is a risk-averse person, so the way we draw graph will look like this. So here, we have W here, and then we have U here. Okay, so the risk-averse person, the graph is concave, like this, yeah? And if we take 2 points, we join those 2 points, then we get something like this. So here, let's say W1. Here, let's say W2. And then the EW, where is it? W1 here is A actually. W2 here is B. Okay? So let me change it so that you're not confused. So A and B. A is what? A is 9. B is what? B is 81. Alright. Now, so we know that in if we have the average, then we have EW here between these two using this. You get what I mean here? So EW here is 59. Okay. Now, previously, before we studied about CE and whatnot here, we know that this is actually what? U, E, G. This is actually what? U, G. But in this case, it is W. Okay? Alright. Now, where you remember when we did our calculation, the main point is to make sure that UW equals to UCE, isn't it? So in that case, UW is here. So where is UCE? UCE has to be here also, isn't it? If UCE is also here, this value, okay, this value is the same for UW and UCE because utility is here, in this case 7. Okay, now, so the question is, where is CE in the graph? Look here, CE is 49, EW is 59. So obviously, at UCE, it hits the curve at this point. Let me use different color, red. At this point, then CE is here, 49. Is it clear? Then, the next question is, where is P in the graph? P in the graph is the distance between E and also CE, isn't it? The expected value of lottery and also the certainty equivalent, which is 49. Then, this distance, called distance capital A and B, AB distance is actually the premium, which is positive. Then this graph confirm with the calculation, because there is no, contradiction in the form of drawing and also calculation, and the curve is concave. That means Ken is a risk-averse person. I hope this is very clear for all of you. You can also try for some other things here, for instance, this and this also. Now, when we talk about attitude of a consumer or decision maker when it comes to uncertainty, we are not only considering about whether they are risk averse, risk loving, or risk neutral people. We are also wanting to know up to what point they are risk averse. Some people are very, very afraid, very, very paranoid that even if you promise them anything, they don't want to involve in any kind of risky, activities. So how to measure this? Okay, so we want to measure how risk averse he is, for instance. So let's look at definition 5. In the definition 5 here, the risk averse person, the magnitude, can be measured by the Arrow-Pratt measure of absolute risk aversion, which is given by this formula. Okay. All right. Now, this formula says that the coefficient of absolute risk aversion is actually the ratio, the negative ratio between second derivative of expected utility of wealth or gamble over first derivative of utility of wealth or lottery or gambling. Okay, don't forget the minus sign here. Now, this Arrow-Pratt measure of absolute risk aversion is also known as coefficient of absolute risk aversion. Coefficient of absolute risk aversion, CARA. All right. Now, let's say we have a simple example to calculate this so that we can interpret the results. So, let's say we have a person, a decision maker named James. Okay. So, here is his preference towards wealth or gambling. Wealth here. So James is actually W to the power of alpha. So his preference towards wealth is W to the power of alpha, such that alpha is between 0 and 1 exclusively. That means alpha here does not include 0 and 1. Now, if we go back to the formula, we know that we need to find two things: the first derivative and the second derivative of James' utility. So the first derivative of James' utility is given by this. This is very simple maths, yeah? Alpha minus 1 can also be rewritten as alpha over W to the power of 1 minus alpha. And obviously, because alpha by condition given here is between 0 and 1 exclusively, then the whole expression that we get here is positive. And we need to find the second derivative of James' utility. So this becomes very simple. Alpha, and then you look here, 1 minus alpha minus, because it's equivalent to alpha minus 1. Yeah? And W to the power of alpha minus 2. It can also be rewritten as this: 1 minus alpha over W2 minus alpha. Right. Now, let's find the coefficient of risk aversion. So the coefficient of risk aversion, if I may rewrite it again, it is U double prime for James over U prime for person named James. So, and we have minus sign. So don't forget minus sign here, and then take the answer for the first derivative that we already found. Rewrite it again here. We get alpha w to the power of alpha minus 1. Take the second derivative, put it back here and on the denominator. So we have minus alpha, 1 minus alpha. Let's extend this line. And w to the power of alpha minus 2. Cancel, 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 cancel. So this one can also be cancelled. I think I make a mistake here. It should be the other way around. Let me fix it, yeah? Otherwise, you're gonna get a wrong answer here. So I need to get my eraser. Let me erase this. This is a huge mistake. So if you have a huge mistake here, your answer will be invalid. And the explanation is also invalid. Now anyway, so should take u double prime j. Let's write it here. Minus alpha 1 minus alpha, w to the power of alpha minus 2, and then on the denominator, take the first derivative of James' utility, which is alpha times w to the power of alpha minus 1. Okay, minus meets minus, positive, alpha cancel, okay, and then becomes minus 1. So simplify it further. What you get here is basically 1 minus alpha over w. Now 1 minus alpha, by condition alpha is between 0 and 1, therefore 1 minus alpha is positive, w itself is positive, so the whole coefficient here is positive. Then if it is positive, what does it mean here? If it is positive, then the person is a risk-averse person. Now let's imagine if the answer here is 0.5 for person A, and let's say the answer here for another person with different types of utility function, maybe like 1.5 or 2 and whatnot, let's say person B. So you can see here we have larger error prep measure or larger coefficient of absolute risk aversion for person B compared to person A. So for person B here, he has a lower certainty equivalent, and because he is a risk averse person, so he is willing to accept fewer gambles, isn't it? Because the higher the magnitude of your risk aversion, the more skeptical you are when it comes to gambling. If you are a very adventurous person and you like hiking, climbing mountain and whatnot, no matter how hard it is, then we can see that, of course, you still have that kind of, fear feeling, because going to the jungle, going to the wood is not easy, basically, yeah. But your level of risk averse is not as high as another person. So for you to take the risk, it's very easy to climb the mountain, for instance, because you already have some information about what should be done, what kind of training, and your health status is also good. However, if the person is a very high, having high risk aversion magnitude in terms of R here, then you can see that he is not that willing to accept, your offer to climb the mountain. Okay, so this is non-economic example. You try to relate it with the value here. All right, now, so what I said here just now is basically this, yeah. Decision makers with a larger error prep measure or coefficient of absolute risk averse, okay, are willing to accept fewer gambles. And additionally, or furthermore, this kind of person, if he has a larger error prep measure, then he has a lower certainty equivalent. And that certainty equivalent is actually, if you go back to the exercise that we did earlier, you can see clearly that the certainty equivalent for this person is 7. Okay, but the we go here, the expected value, the utility is 7, isn't it? And the certainty equivalent is 49, but then the value that we have for the expected value of the wealth itself is 59, which is above CE. All right, so this guy is actually, risk averse person. If you don't believe me, then you try to calculate his R. What do you get? Okay, because you know that U is given by W to the power of half, or this one. Then try to get this, and then see what happens to the value. Okay, then you know that if you get the final answer, you will see that this person is a risk averse person. Now, so here, so we have positive for our example. Okay, so that person is risk averse. But if you have 0 for the answer, then this person is a risk neutral person. If you have negative, then this person is a risk loving person. Okay, so you can see clearly that the Arrow-Pratt measure of absolute risk aversion, or the coefficient itself, is basically the value itself depends on the utility function that we have here, the curvature. Okay, so if U double prime is very high, and then obviously it gives you the higher value in absolute term and whatnot. Okay, also this coefficient, the Arrow-Pratt coefficient here, or the coefficient of absolute risk aversion, is basically unaffected by any positive affine transformation of the utility function. So that means U double prime W is not, the curvature is not affected by any positive affine transformation. Therefore, R is also not affected by any positive affine transformation. Or in other words, the coefficient here, the Arrow-Pratt measure here, is invariant under positive affine transformation of U. So this is really a property of the preferences, isn't it? So the next thing here, let me repeat again this thing. So like I said earlier, the decision makers with a larger Arrow-Pratt measure have a lower certainty equivalent and are willing to accept fewer gambles. So what's the proof of this? Now, I did mention to you that they have lower certainty equivalent when this person is a risk-averse person based on this example. But this is not a proof, this is just an exercise. So what you need to do is to find the proof for this. Okay, proof for this last statement here. This is the last statement. The proof for this is very famous actually, and you can always find it on the internet. The problem is that whether, although you can see a lot of proof on this statement, but then when you see them, do you understand it or not? Okay, do you understand them or not? So that's your homework for you to try. I may ask you in the assignment, I may ask you in the quiz. Okay, so don't take it for granted. You must try. Otherwise, you will never learn how to prove something by yourself. Okay, now, so here, let's move on. So the Arrow-Pratt measure of absolute risk aversion typically varies with wealth. Let's look at this example. So you can see here, let me rewrite it again. Okay, and actually I have written it here in advance. So here, up to that point, only this bit. It varies with the level of wealth. How do we know? Because as you can see here, because R that we found earlier is 1 minus alpha over W. As you can see, W is here, so R depends on W. And if W increases, because W is on the reciprocal, or the denominator, then R reduces. How do we know? Formally, we need to take the first derivative of R with respect to W. Then you find that you see minus sign here, and then 1 minus alpha is positive by condition of alpha between 0 and 1. W squared itself is positive, and then the whole thing is negative. So we can see that R depends on W, and for this specific case of risk averse person, it is negative. So here, let's look at it one by one. A von Neumann-Morgenstern utility function or expected utility function is said to display constant absolute risk aversion over some domain of wealth, if you have some amount of wealth. If what? If over that amount of wealth, that interval, the error prep measure remains constant. So for instance, if you get the answer here equivalent to, let's say, alpha, and alpha is between 0 and 1, obviously alpha is a constant, a scalar, isn't it? So because it is a constant, then we know that the R here is constant, then we know that the von Neumann Morgenstern utility function is a constant function. Okay, then that person is actually having a constant effect of wealth on his R here. On the other hand, if von Neumann utility function is decreasing over some domain of wealth, then that person coefficient is basically absolute risk aversion is decreasing, then the absolute risk aversion, or R here, displays what? Displays a negative relationship with the increase in wealth. So this, the second one here, okay, is the one that we have for our example here. This one, can you see? As wealth increases, the coefficient of risk aversion for the von Neumann utility function of that person is decreasing. So we have negative relationship, isn't it? Okay. Now, and for the risk-loving person, the opposite will hold. Okay. So here, basic idea, let me do it this way. Let's say we have condition. Okay. If we have condition of increasing absolute risk aversion, IRA, then this means as wealth increases, okay, this person holds fewer pounds sterling or ringgit or dollar in risky asset. Okay, that means R prime here is basically positive. But for a constant absolute risk aversion, as wealth increases, he holds the same amount of wealth in the form of pound or ringgit or whatever. Then in this case, he has this, isn't it? And lastly, we have decreasing absolute risk aversion. If the von Neumann Morgenstern utility function possesses decreasing absolute risk aversion, okay, within some domain of wealth, within certain amount of wealth here. So here, when wealth increases, what happens here is that he will hold more dollars or more pounds sterling, in risky assets. Okay, so in this case, we have R prime here less than 0. And then this is more sensible, yeah. The decreasing absolute risk aversion, DARA, is often a sensible assumption. You see here, like the way I interpreted just now, when a person's wealth increases, when a decision maker's wealth increases, say he would be willing to put more money in risky asset, isn't it? So in that sense, the R here is negative. Okay. Here, what is more sensible in terms of assumption? Because we have number one, number two, number three. Just imagine number one, the more wealth you hold, the less your intention to put in risky asset. Number two, the more wealth you hold, there is no change of the amount of money you want to put in the risky asset. But the third one, the more wealth you have, the more is your willingness to put money or to put any kind of wealth, your houses and whatnot, in the risky asset. So number three is a sensible assumption, isn't it? Because the more wealth you have, so you're not that worried about losing, so much wealth because you still have the remaining saving, for instance. So you may allow yourself to put substantial amount of wealth into investment of risky asset. All right. Now, like I said earlier, the R prime will be less than 0 or negative. And so for this person, this example, as you can see, look at this. Let me highlight it here. The R prime, this is the R prime, is negative, isn't it? You know that this person is a risk-averse person because based on the answer here, is positive. The R itself is positive. And you know that the R prime is negative based on this answer. So this person is a risk-averse person. So he is not willing to put himself into a risky asset if he doesn't have enough money or wealth or other form of wealth. Therefore, his R prime here is negative. It has, the risk aversion magnitude or the coefficient is negatively related to wealth. That means, okay, if we were to interpret this result in relation to the last point that I talked to you just now, number 3, let's go back to this. That means the higher the wealth he has, the lower will be his risk aversion attitude toward risky asset. And then that makes sense, isn't it? So that's why you can see the last second point here, decreasing absolute risk aversion is often a sensible assumption. All right, so that is all for this topic, uncertainty in relation to the consumer theory. Of course, by looking at the way I explain it, it seems that it's not a long, lecture. But to be honest with you, if you don't understand the basic about uncertainty and its assumption and also the axioms or the properties of, expected utility function, then it's very hard for you to understand the whole thing. So I advise you to do a lot of exercises. Like I said previously, in my video of Q&A or other videos, what you need to do is, if you don't understand the whole thing here, obviously, because the whole thing here, especially the first bit here, when you see this, and then this formula or this kind of, mathematical, notation and whatnot like this, what you can do here is that first, you go to the very basic thing in economics about uncertainty. at the undergraduate or first degree level of syllabus of microeconomics, you will introduce about 3 different people: risk averse, risk neutral, and whatnot. Try to understand these terms clearly, and then after that, go to the intermediate level, find the videos of YouTube that teach intermediate level of microeconomic on this, and then slowly move to a bit higher and then go to this lecture note. Yeah, and then this lecture note, if you are very hardworking in searching other types of lecture note on the internet and also from the book, that you can find, some similarity in terms of explanation, that you can try to compare and contrast so that you can have a better understanding on uncertainty in relation to the consumer theory. There are a lot of exercises on the internet on this. In fact, some lecturers around the world, apart from putting questions, they also put answer keys. Okay, but not for my case, yeah, because different university has different policies on this. Right, so try to look at them, try to understand them. Of course, the notation won't be the same as the ones that I'm using currently here, but I hope you can still get some basic idea about the expected utility function, the expected the preferences over one gamble to another gamble, and the difference between outcome and also the gambles and the gambling process, and and the preferences, properties, and whatnot. All right, so that's all for this chapter. Thank you very